Tonight, I'm going to show you something that will fundamentally change how you see our cosmic neighborhood. Every diagram of the solar system you've ever seen has been lying to you. Not intentionally, but necessarily. Because the truth is so extreme that if we showed you reality, you wouldn't be able to see anything at all. Here's what nobody tells you. If the sun were the size of a basketball, Earth would be a tiny speck 80 feet away, and Neptune, half a mile away. Everything in between, nothing. Empty. Void. The solar system isn't a cozy family of planets, it's an abyss with occasional specks of matter floating in the darkness. And by the end of this journey, you'll never look at the night sky the same way again. Before we dive in, if you find this kind of deep exploration fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it means everything to me for keeping these journeys going. Now, let's begin. The lie we've been told, understanding the true distances. Close your eyes for a moment and picture the solar system. What do you see? Probably something like this. The sun in the middle, nice and round. Mercury close by. Venus a bit further. Earth with its moon. Mars with its reddish tint. Then the asteroid belt. A dense ring of rocky debris. After that, the giant planets. Jupiter with its red spot. Saturn with its magnificent rings. Uranus and Neptune in the outer reaches. All of them relatively close together, all visible in a single glance. This image is burned into our minds from childhood. We've seen it in textbooks, on posters, in movies, in documentaries. It's comforting. It makes the solar system feel like a family, with all the planets as siblings orbiting around their parent star. But this image is a lie. Not a malicious lie, but a necessary one. Because if textbooks showed the solar system to scale, if they showed the actual distances between planets relative to their sizes, you wouldn't see anything. The planets would be invisible specks separated by vast empty pages. An accurate diagram of the solar system would require a poster stretching for miles. Even then, the planets themselves would be too small to see without a magnifying glass. The solar system is not a crowded place. It's an emptiness of almost incomprehensible proportions. Space is called space for a reason. It's mostly nothing. And understanding this nothingness is essential to understanding our place in the cosmos. Humans didn't always know this. For most of history, people believed the universe was small and cozy. The ancient Greeks thought the stars were fixed to a crystalline sphere just beyond the moon and planets. The entire cosmos, in their view, might have been only a few million miles across. Earth sat at the center, and everything revolved around us in neat, concentric circles. This geocentric model persisted for nearly 2,000 years. It wasn't until 1543 that Nicholas Copernicus proposed a radical idea. The Earth orbits the Sun, not the other way around. Even then, Copernicus didn't grasp the true scale. He knew the Sun was the center, but he still imagined the solar system as relatively compact. Johannes Kepler, working in the early 1600s, made the next breakthrough. By carefully analyzing the orbital data of Mars, he discovered that planets move in ellipses, not perfect circles. He also derived mathematical laws relating a planet's orbital period to its distance from the Sun. For the first time, astronomers could calculate relative distances within the solar system. They knew that Jupiter was about 5 times farther from the Sun than Earth, that Saturn was about 10 times farther. But they still didn't know the absolute scale. They didn't know how far one was. That changed in 1672, when the Italian astronomer Giovanni Cassini organized an expedition to measure the distance to Mars using parallax. By observing Mars from two different locations on Earth simultaneously, Paris and French Guiana, and measuring the tiny shift in its apparent position, Cassini could calculate its distance using trigonometry. From that, he could work out the distance from Earth to the Sun. His answer? About 87 million miles. Not perfect, but remarkably close to the modern value of 93 million miles. For the first time, humanity had a sense of the true scale, and it was shocking. 93 million miles. The number seems almost quaint now, but in the 17th century, it was staggering. The entire Earth, every continent and ocean, could be crossed in months of sailing. But the distance to the Sun was tens of thousands of times larger than the circumference of the Earth. The solar system was vastly, incomprehensibly bigger than anyone had imagined. And we've only learned more since then. Every improvement in measurement technology has revealed the solar system to be even larger, even emptier than the previous generation believed. Let me start by telling you about scale. Because human beings are terrible at understanding scale. We evolved on the African savanna where the distances that mattered were measured in steps, in throws, in how far we could see before the horizon curved away. Our brains developed to handle distances from a few inches to a few miles. Beyond that, everything becomes abstract numbers that we can manipulate mathematically but can't truly feel. Psychologists have studied this phenomenon extensively. They call it scope insensitivity or scope neglect. Our emotional response to larger numbers doesn't scale proportionally with the numbers themselves. Studies have shown that people feel roughly the same emotional reaction to hearing about a disaster that killed 100 people as they do to one that killed 1,000 or even 10,000. The numbers are different, but our gut response is similar. Beyond a certain point, numbers become abstract. They stop feeling real. The same thing happens with distances. When I tell you that the Sun is 93 million miles from Earth, what does that mean to you? Can you picture 93 million miles? Can you feel it in your bones? Of course not. It's just a big number. It might as well be 1,000,000 miles or 1,000,000,000 miles. All those numbers exist in the same mental category, really far away. This is a fundamental limitation of human cognition. Our ancestors needed to judge distances they could walk in a day, distances to pray, distances to water sources. They didn't need to comprehend millions of miles. Evolution didn't equip us for cosmic scales. This is why understanding the solar system requires analogies. We need to shrink things down to human scales before we can grasp them. And when we do that, when we shrink the solar system to something we can hold in our hands, the true nature of space reveals itself. Let's start with our anchor point, the Sun. The Sun is enormous. It contains 99.86% of all the mass in the entire solar system. Everything else, all the planets, moons, asteroids, comets, dust, everything, makes up just 0.14%. The Sun is so dominant that calling our cosmic neighborhood a solar system is almost an understatement. It's really just the Sun with some debris. The Sun has a diameter of about 864,000 miles. That's about 109 times the diameter of Earth. If the Sun were hollow, you could fit approximately 1.3 million Earths inside it. Think about that. Take the Earth with all its continents and oceans, all its mountains and valleys, every city and forest and desert. Now, imagine making 1.3 million copies of it and stuffing them all inside the sun. That's how big our star is. The sun is so massive that it accounts for 99.86% of the solar system's total mass. Jupiter, the largest planet, contains most of the remaining mass. All the other planets, moons, asteroids, and comets together make up a tiny fraction. If the solar system were a pizza, the sun would be the entire pizza except for a few crumbs. Jupiter would be the largest crumb. Earth wouldn't even be visible. But let's make this more tangible. Let's shrink the sun down to something we can hold. Let's make the sun the size of a basketball. A standard basketball has a diameter of about 9.4 inches. If the sun were a basketball, what size would the Earth be? Earth would be the size of the head of a pin. About 0.086 inches in diameter. Smaller than a BB. Smaller than a peppercorn. It would be a tiny speck, barely visible to the naked eye. Now here's where it gets interesting. In this scale model, how far apart would the basketball sun and the pinhead Earth be? 26 yards, not 26 inches, not 26 feet, 26 yards, nearly 80 feet, almost the length of a basketball court. If you stood on one end of a basketball court holding a basketball representing the sun, and someone stood near the other end holding a tiny pinhead representing Earth, that would be roughly accurate to scale. The space between you would be empty. Just air. Nothing else. Let that sink in. A basketball and a pinhead separated by 80 feet of nothing. That's the sun and Earth. And that's just Earth. The planets closer to the sun are obviously closer, but not by much in the grand scheme of things. Mercury, the innermost planet, would be about 10 yards from our basketball sun in this scale model. 10 yards is 30 feet. Mercury itself would be a tiny speck, even smaller than Earth, about the size of a grain of sand. A grain of sand 30 feet from a basketball, and between them, nothing. Vacuum, void. Mercury is a small, dense world covered in craters. It has almost no atmosphere because its gravity is too weak, and its proximity to the sun too close. Any gases that might accumulate are stripped away by the solar wind. The surface temperature swings wildly from over 800 degrees Fahrenheit on the sun-facing side to negative 290 degrees on the night side. It's a hostile world, baked and frozen in turns, and yet, despite being the closest planet to the sun, Mercury is isolated, alone in its bubble of space. If you stood on Mercury's surface, you would see the sun dominating the sky, about 3 times larger than it appears from Earth. But looking away from the sun, you would see nothing but black sky and stars. No nearby companions, no sense of being in a neighborhood. Just a small rock orbiting a nuclear furnace in the middle of an infinite darkness. Venus would be about 19 yards from our basketball sun, 57 feet. Another tiny speck, slightly smaller than Earth. Venus is often called Earth's twin because they're similar in size, but the resemblance ends there. Venus has a thick atmosphere of carbon dioxide that traps heat through a runaway greenhouse effect. The surface temperature is about 900 degrees Fahrenheit, hot enough to melt lead. The atmospheric pressure is about 90 times what we experience on Earth, equivalent to being 3,000 feet underwater. Sulfuric acid clouds blanket the planet. No human could survive on Venus unprotected for even a moment. And between Venus and Mercury, empty space. About 27 feet in our scale model. Nothing there, no asteroids, no debris, no landmarks, just void. Earth at 26 yards from our basketball sun, our home, a tiny pinhead in the darkness, Mars would be about 40 yards from our basketball sun, 120 feet, and Mars itself, a pinhead about half the size of Earth's pinhead. Mars is smaller than Earth, about half the diameter. It has a thin atmosphere, only about 1% of Earth's atmospheric pressure. The planet is cold, with average temperatures around -80 degrees Fahrenheit. It has polar ice caps made of frozen water and carbon dioxide. Ancient riverbeds suggest water once flowed on its surface, but today, Mars is a frozen desert. The distance from Earth to Mars varies enormously depending on where both planets are in their orbits. At closest approach, Mars is about 33.9 million miles from Earth. At its farthest, when the Sun is between us, Mars is about 250 million miles away. In our basketball scale model, that's a difference of about 11 feet to about 83 feet. Even at its closest, Mars is profoundly far. Light takes about 3 minutes to travel from Earth to Mars at closest approach. Over 22 minutes at farthest. Any message we send to a Mars rover takes that long to arrive, and any response takes equally long to return. The inner solar system, the 4 rocky planets closest to the Sun, would fit within about 40 yards of our basketball. But remember, the planets themselves are specks. The overwhelming majority of that space is empty. If you were transported to a random point between Mercury and Mars, picked completely at random, you would almost certainly find yourself in empty space. Not close to any planet, not even close to any asteroid. Just floating in darkness with the Sun as the distant bright point, and the stars as your only other companions. And we haven't even gotten to the outer solar system yet. Let me give you another way to think about this. Light travels at approximately 186,000 miles per second. That's the fastest anything in the universe can travel. Light is so fast that it can circle the Earth's equator about 7.5 times in a single second. From the Sun to Earth, light takes about 8 minutes and 20 seconds. That's how far away we are. Even at the fastest speed possible in the universe, it takes over 8 minutes to make the journey. Now, the Sun is enormous. It's 864,000 miles across. Light can cross the Sun's diameter in about 4.6 seconds. But crossing the distance from the Sun to Earth takes 8 minutes and 20 seconds. The empty space between us is about 108 times larger than the Sun itself. The Sun, as massive as it is, as dominant as it is in our solar system, is a tiny point compared to the distances involved. This is the fundamental truth we need to understand. The objects in our solar system are small. The spaces between them are immense. The ratio is so extreme that our diagrams have no choice but to lie to us. Think about what this means for our everyday experience. When you look up at the sky on a clear night and see the stars scattered across the darkness, you're seeing points of light separated by incredible distances. But even within our own solar system, even among our closest cosmic neighbors, the same emptiness prevails. If you were somehow floating in space halfway between Earth and Mars at their closest approach, you would see nothing in any direction. The Sun would be a bright point of light in the distance, not the enormous glowing orb we're used to seeing from Earth. And Mars and Earth would be invisible to the naked eye, too small and too far away to see without a telescope. The solar system is dark. The solar system is empty. The solar system is cold. These are the truths that diagrams hide from us. Let me continue building our scale model because the outer solar system is where things get truly mind-bending. In our basketball sun model, we established that Earth is about 26 yards away as a tiny pinhead. Now let's continue outward. The asteroid belt, which many people imagine as a dense field of rocks where spaceships have to dodge and weave, sits between Mars and Jupiter. In our scale model, the inner edge of the asteroid belt would be about 55 yards from our basketball sun, and the outer edge would be about 85 yards away. But here's the thing about the asteroid belt that movies get completely wrong. It's not a dense field of anything. The asteroid belt contains millions of asteroids, yes, but those asteroids are spread across such an enormous volume of space that if you flew through the asteroid belt, you would almost certainly see nothing. The average distance between asteroids in the belt is about 600,000 miles. In our scale model, that translates to asteroids being separated by several feet on average, and each asteroid would be smaller than a grain of sand. The odds of encountering anything by accident are astronomically small, because the space is almost entirely empty. The asteroid belt, despite its dramatic name, is yet another vast emptiness with occasional tiny specks of rock. Jupiter, the king of planets, would be in our basketball model about 143 yards from the Sun. That's nearly 1.5 football fields away. And Jupiter itself, despite being the largest planet in the solar system, in our scale model, it would be about the size of a marble, just under an inch in diameter. A marble, sitting 1.5 football fields away from a basketball. In between, nothing. Empty space. Saturn would be about 263 yards from our basketball sun. That's over 2.5 football fields. Saturn, with its magnificent rings, would be about 3/4 of an inch across in our model. A small marble, surrounded by rings so thin they'd be essentially invisible at this scale. Uranus would be about 530 yards away, more than 5 football fields from the Sun. A tiny speck about 1/3 of an inch in diameter. Neptune, the most distant planet, would be about 830 yards from our basketball sun. That's nearly 1/2 mile away. And Neptune itself would be about 1/3 of an inch in diameter. Slightly smaller than Uranus. Let's pause here and take stock of what we've built. In our scale model where the Sun is a basketball, the entire planetary solar system, from Mercury out to Neptune, stretches for nearly 1/2 mile. And within that 1/2 mile, we have one basketball, 2 tiny pinheads for Mercury and Venus, one slightly larger pinhead for Earth, a slightly smaller pinhead for Mars, millions of invisible sand grains spread across 30 yards for the asteroid belt, a marble for Jupiter, a smaller marble for Saturn, and 2 specks for Uranus and Neptune. That's it. The rest, the overwhelming majority of that 1/2 mile, is empty space. Nothing. Void. The total volume of all the planets combined, even including massive Jupiter, is tiny compared to the volume of space they occupy. If you added up the diameters of all 8 planets and laid them end to end, you get about 249,000 miles. That sounds like a lot until you realize that the diameter of Neptune's orbit is about 5.6 billion miles. The planets themselves take up less than 0.005% of the diameter of the solar system. And we haven't even discussed the space above and below the orbital plane. The solar system is usually shown flat, with all the planets in a disk, but space extends in all directions. The emptiness is 3-dimensional. The void extends above you and below you, as well as in every horizontal direction. If you were somehow transported to a random point within Neptune's orbit, picked completely at random, you would almost certainly find yourself in empty space. No planets visible, no asteroids nearby. Just darkness and cold and silence. This is the true nature of our solar system. I want to emphasize something about light travel times, because they really drive home the emptiness. We mentioned that light from the sun takes about 8 minutes and 20 seconds to reach Earth. Let's extend that. Light from the sun takes about 3 minutes to reach Mercury, the closest planet. To Venus, it's about 6 minutes. To Mars, about 12.5 minutes. To Jupiter, 43 minutes. To Saturn, 1 hour and 19 minutes. To Uranus, 2 hours and 40 minutes. To Neptune, 4 hours and 10 minutes. If the sun suddenly went dark, if something happened and it stopped emitting light right now, Neptune wouldn't know for over 4 hours. For those 4 hours, Neptune would continue to be illuminated by light that left the sun before it died. 4 hours of phantom sunlight crossing empty space. These light travel times tell us something profound about the emptiness of space. Light is the fastest thing in the universe, and it takes hours to cross our solar system. Nothing else can go faster. Any spacecraft, any theoretical future technology bound by the laws of physics, would take even longer. The emptiness isn't just spatial, it's temporal. The distances aren't just far, they're time itself, stretched across the void. When we look at Neptune through our telescopes, we're seeing it as it was 4 hours ago. We're looking into the past because the light carrying information from Neptune takes that long to reach us. The solar system isn't just big in space, it's big in time. But here's what's truly remarkable. Everything we've discussed so far, from the sun out to Neptune, represents only a tiny fraction of the solar system's true extent. Most people think Neptune marks the edge of the solar system. It doesn't. Not even close. Neptune is where the major planets end, but the sun's gravitational influence extends vastly further. The true edge of the solar system is defined by the Oort cloud, a spherical shell of icy objects that surrounds our solar system at distances up to 2 light years away. 2 light years. If light from the sun takes 4 hours to reach Neptune, it takes up to 2 years to reach the outermost objects of the Oort cloud. In our basketball scale model, where Neptune is about half a mile from the sun, the outer edge of the Oort cloud would be about 2,000 miles away. That's roughly the distance from New York to Las Vegas. The entire continental United States could fit between our basketball sun and the edge of our solar system, and almost all of that space is empty. The Oort cloud isn't a dense shell, it's a sparse scattering of icy bodies, each separated by millions of miles, drifting in cold darkness at the very limit of our sun's gravitational reach. The solar system isn't just mostly empty, it's almost entirely empty. The objects we think of when we picture the solar system, the sun and planets and moons, they're not the main feature. They're incidental. Decorations scattered across an abyss. Let's talk about what would happen if you actually tried to see the solar system to scale. Several scientists and educators have built scale models of the solar system, and the results are always humbling. In 2015, filmmakers Wiley Overstreet and Alex Gorosh created a scale model of the solar system in the Black Rock Desert of Nevada. They used a marble about the size of Earth to represent Earth. At that scale, the sun was about 5 feet across, a large glowing sphere. The entire model stretched across 7 miles of desert. 7 miles. That's how far you have to walk to go from the sun to Neptune when Earth is the size of a marble. In this model, Mercury was about 170 feet from the sun. Venus was about 320 feet. Earth was about 430 feet. Mars was about 650 feet. So far, maybe manageable for a casual walk. But then Jupiter was about half a mile away. Saturn was almost a mile away. Uranus was over 2 miles away. And Neptune was over 3.5 miles from the Sun. The filmmakers drove between the planets because walking would have taken too long. Even driving, the sense of emptiness was overwhelming. Minutes would pass between planets. The landscape stretched flat and featureless. The Sun, despite being a 5-foot glowing sphere, was just a tiny point of light when viewed from Neptune's position. This is what accurate looks like. This is what the solar system actually is. Miles and miles of nothing with occasional tiny objects separated by so much space that the human mind struggles to comprehend it. There are other scale models around the world. The Sweden solar system stretches across the entire country, with the Sun represented by the Ericsson globe in Stockholm and the planets scattered across Swedish cities and towns. Neptune is represented by a sculpture about 230 kilometers from Stockholm in Söderhamn. Pluto is represented in Delsbo, about 300 kilometers from Stockholm. And the termination shock, where the solar wind begins to slow, a small exhibit in Kiruna, over 950 kilometers from the Sun. 900 kilometers. That's over 550 miles, to represent just the inner boundary of interstellar space. These models exist not because they're convenient, but because they're the only way to tell the truth. Any diagram that fits on a page, any illustration in a textbook, any animation in a documentary, they all lie by necessity. The truth doesn't fit. The truth is vast and empty and cold. The Great Void, journey through the outer solar system. Imagine you're aboard a spacecraft, departing from Earth. You've said your goodbyes, completed your training, and now you're heading out into the solar system. Your destination is Neptune, the most distant major planet. As you leave Earth orbit, you look back. The Earth is a blue marble, just as the astronauts described it. Beautiful, vibrant, alive. You can see the continents, the oceans, the swirling white of clouds. It's home, and it's getting smaller by the second. Within a few hours, Earth has shrunk to the size of a marble, then a pea, then a dot. Eventually, even with your best optical instruments, it becomes difficult to distinguish from the stars. Your home planet, with all its billions of people, all its cities and forests and oceans, has become a point of light. One point among many. And you're still in the inner solar system. You haven't even gotten to Mars yet. The Sun remains the dominant feature of your view, but it's already smaller than you're used to seeing it from Earth. As you continue outward, it shrinks further. Not dramatically at first. The changes are gradual, but day by day, week by week, the Sun gets smaller. The light it casts becomes noticeably dimmer. The warmth you feel on the sun-facing side of your spacecraft decreases. You're moving away from the source of all warmth in your cosmic neighborhood. Around you, in every direction except toward the Sun, is darkness. Not the darkness of a moonless night on Earth, where the sky is still filled with visible stars. This is a deeper darkness. Yes, stars are visible. They're actually clearer than they would be from Earth, because there's no atmosphere to blur them. But they're just points of light, impossibly far away. They offer no companionship, no sense of proximity. You're not traveling toward them. They're the backdrop, not the destination. The psychological weight of this journey would be immense. Human beings evolved in environments full of life, full of movement, full of other creatures. We are social animals designed for a world of trees and grass and other humans. The vast emptiness of interplanetary space offers none of this. Just you, your spacecraft, and an infinite black void. Astronauts who have traveled even to the moon, a mere 3 days away, have described the profound loneliness of seeing Earth shrink behind them. Michael Collins, who orbited the moon alone while Armstrong and Aldrin walked on the surface, described feeling cut off from all of humanity. He was behind the moon, out of radio contact with Earth for 47 minutes during each orbit. During those periods of silence, he was the most isolated human being who had ever lived, separated from everyone else in existence by the bulk of another world. But the moon is close, incredibly close by solar system standards. A journey to Neptune would take years, not days. The isolation would be beyond anything any human has ever experienced. There would be no quick return if something went wrong. No rescue mission could reach you. You would be utterly, completely alone with your crewmates, suspended in a void that stretches in every direction. After several weeks of travel, you approach the orbit of Mars. The red planet should be somewhere nearby. But here's the thing the diagrams don't prepare you for. You probably can't see it. Mars, at its brightest as seen from Earth, is a tiny red dot. From a spacecraft passing through its orbital region, it might be millions of miles away, somewhere along its own orbit around the Sun. Unless your trajectory is specifically designed to encounter Mars, you'll pass through its orbital zone and see nothing but empty space. This is a crucial point. The planets don't fill their orbits. They're tiny objects tracing paths through enormous volumes of space. Mars's orbit is a circle about 900 million miles in circumference. Mars itself is about 4,200 miles across. The planet is less than 1/200,000th of its own orbital path. If you picked a random point on Mars's orbital track, the chance of Mars being nearby would be essentially zero. You might detect Mars with your instruments, a radar ping returning from a rocky surface millions of miles away, an infrared signature slightly warmer than the surrounding space, but visually, nothing. Just black sky and distant stars. The asteroid belt comes next. This is where the movies prepare you for excitement. You imagine dodging tumbling rocks, navigating through a field of debris, pilots gripping their controls, and executing fancy maneuvers. You've seen the scenes in countless science fiction films. The hero weaving between spinning boulders, the villain's ship smashing into an asteroid, the tension of threading through a cosmic obstacle course. The reality is profoundly different. You enter the asteroid belt and nothing happens. Days pass, weeks pass. You see no asteroids. Your instruments occasionally detect one at vast distances, millions of miles away, too small and too far to see with the naked eye. The asteroid belt, far from being a crowded field, is emptier than any desert on Earth. It's emptier than the Pacific Ocean. It's emptier than you could possibly imagine. The asteroid belt contains roughly 1.1 to 1.9 million asteroids, larger than 1 kilometer in diameter. That sounds like a lot, but those asteroids are spread across a volume of space so enormous that the numbers become almost meaningless. The belt occupies a donut-shaped region between about 2 and 3.3 astronomical units from the Sun. The total volume is about 2.8 times 10 to the 21st cubic miles. Do the math, and you find that the average asteroid is surrounded by about 10 billion cubic miles of empty space. The density of material in the asteroid belt is essentially zero. It's a belt in name only. If you wanted to actually see an asteroid, You'd have to aim for one specifically. Ceres, the largest object in the belt, is about 590 miles across. Vesta, the second largest, is about 326 miles. Pallas is about 318 miles. These are the giants of the asteroid belt, and they're scattered across millions of miles of space. The average distance between any two sizable asteroids is about 600,000 miles. That's more than twice the distance from Earth to the Moon. And most asteroids are far smaller than Ceres or Vesta. Most are just rocks, a few hundred feet or a few miles across, invisible except at close range. Scientists have sent 9 spacecraft through the asteroid belt without incident. The Dawn mission traveled through it twice on its way to Vesta and Ceres. The Juno mission crossed it on its way to Jupiter. Galileo crossed it. The New Horizons spacecraft crossed it on its way to Pluto. None of them had to dodge anything. None of them even came close to hitting anything by accident. The asteroid belt is, for all practical purposes, empty space with occasional very widely scattered rocks. The Hollywood version of the asteroid belt exists because it makes for better cinema. The reality wouldn't translate well to screen. Hours of black space, days of nothing. The dramatic tension of navigating through absolutely nothing at all. You emerge from the asteroid belt after months of travel, having seen nothing of it. Ahead lies Jupiter. Jupiter is the king of planets. It contains more mass than all the other planets combined. In fact, if you gathered up Mercury, Venus, Earth, Mars, Saturn, Uranus, Neptune, and all the moons and asteroids and comets and Kuiper belt objects, and weighed them all together, Jupiter would still be more than twice as heavy. Its diameter is about 86,800 miles, roughly 11 times Earth's diameter. Its volume could contain over 1,300 Earths. Its Great Red Spot, a storm that has raged for at least 350 years and probably much longer, is larger than Earth itself. You could drop our entire planet into that storm, and it would disappear like a stone thrown into an ocean. Jupiter has at least 95 known moons, and astronomers keep discovering more. 4 of these moons are large enough to be considered worlds in their own right. These are the Galilean moons, named after Galileo Galilei, who discovered them in 1610 using one of the first telescopes. When Galileo saw these 4 points of light moving around Jupiter, he realized that not everything in the sky orbited Earth. It was one of the key observations that helped overturn the geocentric model of the universe. From Earth, Jupiter is one of the brightest objects in the night sky, outshining everything except the Moon and Venus. Ancient peoples named it after the king of their gods. The Romans called it Jupiter. The Greeks called it Zeus. The Babylonians called it Marduk. Every civilization that looked up at the sky noticed this bright wanderer and gave it a place of honor. But here's what you experience as you approach it: gradual revelation. For weeks, Jupiter is just a bright point in the sky, slightly different in color from the stars, but not visibly larger. Then it becomes a small disk, then a larger disk. The bands start to become visible, creamy white and rusty orange. The Great Red Spot appears, a dark blemish on the planet's face. As you get closer, Jupiter starts to become genuinely impressive. It fills more and more of your view. The complexity of its atmosphere reveals itself. You can see the swirls and eddies where different colored bands meet. You can see smaller storms, white ovals and brown ovals, each one larger than terrestrial hurricanes. You can see the turbulence at the edges of the Great Red Spot, where winds blow at over 400 miles per hour. Jupiter's atmosphere is a dynamic, churning chaos. The planet has no solid surface. As you descend into its atmosphere, the pressure and temperature just keep increasing. Eventually, the hydrogen that makes up most of Jupiter's bulk becomes so compressed that it behaves like a metal, conducting electricity and generating the planet's powerful magnetic field. The moons become visible as points of light, then as small spheres. Io, with its volcanic surface, is the most volcanically active body in the solar system. More than 400 active volcanoes dot its surface, constantly erupting, constantly resurfacing the moon with sulfur and sulfur dioxide. The surface is a garish palette of yellows, reds, and oranges. Europa is the most intriguing of the Galilean moons. Its surface is smooth ice, crisscrossed with cracks and ridges. Beneath that ice lies a global ocean that may contain more water than all of Earth's oceans combined. Some scientists believe Europa's ocean could harbor life. Hydrothermal vents at the bottom of this alien sea might provide the energy and chemistry needed for organisms to exist. Ganymede is the largest moon in the solar system, even larger than the planet Mercury. It has its own magnetic field, the only moon known to possess one. Its surface is a mix of older, heavily cratered terrain and younger, grooved regions that suggest geological activity in the past. Callisto is the outermost of the large moons, and its surface is ancient, saturated with craters from billions of years of impacts. Unlike the other Galilean moons, Callisto shows little sign of geological activity. It's a frozen museum of the early solar system, its surface a record of bombardment that occurred 4 billion years ago. But even as you pass through the Jovian system, the emptiness persists. Jupiter's moons, despite numbering in the dozens, are spread across enormous distances. Io, the innermost Galilean moon, orbits about 262,000 miles from Jupiter. That's slightly farther than the distance from Earth to our moon. Europa orbits about 417,000 miles out. Between Io and Europa, nothing. Empty space. About 155,000 miles of void. Ganymede orbits at 665,000 miles. Between Europa and Ganymede, nearly 250,000 miles of nothing. Callisto orbits over 1.17 million miles from Jupiter. Between Ganymede and Callisto, over 500,000 miles of empty space. You could fly through the Jovian system and pass relatively close to Jupiter while being millions of miles from any of its moons. The system is structured, yes, organized by gravity, but it's not crowded. The empty space vastly dominates. If you stood on Callisto and looked up at Jupiter, the planet would be an impressive sight. About 4 degrees across in the sky, roughly 8 times larger than the full moon appears from Earth. But looking in any other direction, you would see only stars. Io, Europa, and Ganymede would be too far away to see as anything more than points of light. The Jovian system, home to nearly 100 moons, would feel empty and lonely. After Jupiter, the emptiness deepens. Saturn is about 400 million miles farther out than Jupiter. That's nearly as far as the entire distance from the Sun to Jupiter. The journey from Jupiter to Saturn is almost as long as the journey from the Sun to Jupiter. And during this journey, you see almost nothing. Jupiter shrinks behind you, its moons fading into invisibility, its bulk diminishing to a bright point. Saturn grows ahead of you, but slowly. For months, it's just another point of light, not visibly different from the stars. Only gradually does it become a disk, and only much later do the rings become visible. Between Jupiter and Saturn, nothing. Black space, distant stars, cold, silence. The outer solar system is characterized by these vast gulfs between planets. The distances grow progressively larger as you move outward. The planets become more isolated. Each one sits alone in an enormous bubble of empty space, separated from its neighbors by hundreds of millions or billions of miles. Saturn, when you finally arrive, is breathtaking. The rings are unlike anything else in the solar system. Seen from Earth through a telescope, they're beautiful. Seen from close approach, they're transcendent. Thousands of individual ringlets made of ice and rock, each particle orbiting Saturn in its own path, together creating the illusion of solid bands. The rings extend outward for about 175,000 miles from Saturn's cloud tops. They're composed mostly of water ice with some rocky debris mixed in. The particles range in size from tiny grains to chunks as large as houses. Each particle orbits Saturn independently, but together they form patterns and structures that astronomers have studied for centuries. There are gaps in the rings, created by the gravitational influence of Saturn's moons. The most famous is the Cassini division, a dark gap about 3,000 miles wide, easily visible from Earth through a telescope. But even the Cassini division isn't empty. It contains material, just less densely packed than the main rings. But even Saturn's rings, as spectacular as they are, conform to our theme of emptiness. The rings are extraordinarily thin. They extend outward for about 175,000 miles from Saturn's cloud tops, but they're only about 30 feet thick on average in most places. If you scaled the rings down to the width of a football field, they would be thinner than a razor blade. They're a flattened disk of debris, more gap than substance. The ring particles themselves are separated by empty space. The rings look solid from a distance, but up close, they're individual chunks of ice and rock, each following its own orbit, rarely touching each other. The Cassini spacecraft, which orbited Saturn for 13 years, flew through the gaps between the rings and survived. The rings are another cosmic illusion, appearing dense while being mostly void. Saturn's moon system is equally fascinating and equally empty. Saturn has at least 146 known moons. That sounds crowded, but these moons are scattered across millions of miles. Titan, Saturn's largest moon, is a world unto itself. It's the only moon in the solar system with a thick atmosphere, a dense shroud of nitrogen even thicker than Earth's. You cannot see Titan's surface through this orange haze. The Huygens probe, which descended through Titan's atmosphere in 2005, revealed a landscape of hydrocarbon lakes and icy mountains. On Titan, it rains. Not water, but liquid methane and ethane. These hydrocarbons pool into lakes and seas near the poles. Rivers of methane carve channels across the surface. Titan has a weather cycle similar to Earth's water cycle, but based on hydrocarbons at cryogenic temperatures. It's the only body in the solar system besides Earth where liquid currently exists on the surface. Yet Titan orbits nearly 760,000 miles from Saturn. It takes 15.9 Earth days to complete one orbit. From Titan's surface, Saturn would appear about 11 times larger than the full moon appears from Earth, dominating the hazy sky. Enceladus is a small icy moon only about 310 miles across, but it hides a secret. Geysers at its south pole spray water ice into space, creating a plume that extends hundreds of miles above the surface. The Cassini spacecraft flew through this plume and detected water, organic molecules, and salts. Beneath Enceladus's icy crust lies a global ocean, kept liquid by tidal heating. This tiny moon, smaller than the state of Arizona, is now considered one of the most likely places in the solar system to find life. Yet, Enceladus orbits about 148,000 miles from Saturn, lost in the void between the planet and its larger moons. It takes only 33 hours to complete one orbit, racing around Saturn in the darkness. Between Saturn's moons, as always, empty space dominates. If you picked a random point in Saturn's moon system, you would almost certainly find yourself floating in vacuum, with the nearest solid surface hundreds of thousands of miles away. After Saturn, we enter truly remote territory. Uranus is about 900 million miles farther out than Saturn. The journey would take years, even at the speeds spacecraft can achieve. During this journey, Saturn would shrink behind you, its rings vanishing first, then its bulk fading to a point. Uranus would grow ahead of you, but so slowly that for months you would see no change. Uranus takes 84 Earth years to complete one orbit around the Sun. That means if you were born on Uranus, you wouldn't live long enough to see your first birthday by Uranian standards. A single season on Uranus lasts about 21 years. When Voyager 2 flew past in 1986, the planet's south pole was pointed almost directly at the Sun. It had been summer in the southern hemisphere for decades. Uranus is tilted on its side, rolling along its orbit like a ball. Its axis of rotation is tilted about 98 degrees from vertical. No one knows for certain why Uranus is tilted so dramatically. The most common theory is that a large impactor struck it early in the solar system's history, knocking it over. Whatever the cause, the result is a strange world where the poles sometimes point almost directly at the Sun, while the equator plunges into extended darkness. The planet itself is a pale blue-green, coloured by methane in its atmosphere. It's smaller than Jupiter or Saturn, but still enormous by terrestrial standards, about 4 times Earth's diameter. It has no solid surface, just layers of atmosphere becoming progressively denser until they merge into a slushy mantle of water, methane, and ammonia ices. Uranus has 27 known moons, all named after characters from the works of William Shakespeare and Alexander Pope. There's Titania and Oberon, named after the fairy king and queen from A Midsummer Night's Dream. There's Ariel and Umbriel, named after spirits from the Rape of the Lock. And there's Miranda, named after the daughter of Prospero in The Tempest. Miranda, the innermost of the large moons, has one of the strangest surfaces in the solar system. It looks like a world that was shattered and reassembled, with dramatic cliffs, grooves, and chaotic terrain. Some scientists believe Miranda was indeed broken apart by an impact and gravitationally pulled back together. Others think the bizarre surface is the result of intense tidal heating in the past. Whatever the cause, Miranda is a world of extremes, with cliffs that drop 12 miles from top to bottom, the tallest known cliffs in the solar system. Neptune is another billion miles beyond Uranus. The journey from Uranus to Neptune is longer than the journey from Saturn to Uranus. The distances keep growing. The emptiness keeps deepening. Neptune takes 165 years to complete one orbit. Since its discovery in 1846, it has completed only about one full orbit around the Sun. We are just now seeing Neptune return to the position in space, where it was when humans first found it. Neptune is the windiest planet in the solar system. Wind speeds can reach 1,200 miles per hour, far faster than any winds on Earth. For comparison, the fastest tornado ever recorded on Earth had winds of about 300 miles per hour. Neptune's winds are 4 times faster. These winds drive enormous storm systems across the planet's deep blue face. When Voyager 2 flew past in 1989, it photographed a great dark spot, similar to Jupiter's Great Red Spot. This storm was about the size of Earth, with wind speeds of over 1,500 miles per hour at its edges. But when the Hubble Space Telescope looked at Neptune a few years later, the great dark spot had vanished. Unlike Jupiter's centuries-old storm, Neptune's storms are transient, forming and dissipating over years or decades. New spots have appeared since then, lived for a few years, and then faded away. Neptune has 16 known moons. The largest, Triton, is one of the coldest objects in the solar system, with surface temperatures around negative 391 degrees Fahrenheit. That's cold enough that nitrogen, which makes up most of Earth's atmosphere, freezes solid on Triton's surface. Despite this extreme cold, Triton shows evidence of geological activity. Geysers of nitrogen gas erupt from its surface, leaving dark streaks across the icy terrain. These geysers are driven by solar heating of subsurface nitrogen ice. When the ice vaporizes, it explodes upward through cracks in the crust, carrying dark particles that settle downwind. Triton orbits Neptune backward, in a retrograde direction, suggesting it was captured from the Kuiper Belt rather than forming alongside Neptune. It's slowly spiraling inward toward Neptune. In about 3.6 billion years, it will either crash into Neptune or be torn apart by tidal forces, potentially forming a ring system that would dwarf Saturn's. But even these fascinating worlds are isolated. The space between Uranus and Neptune is staggering, over 1 billion miles of nothing. The Voyager 2 spacecraft, traveling at tens of thousands of miles per hour, took 3.5 years to travel from Uranus to Neptune. 3.5 years of crossing empty space. No landmarks, no milestones. Just the gradual dimming of the sun and the slowly shifting positions of the stars. Beyond Neptune, we enter the Kuiper Belt. This is the realm of Pluto, Eris, Makemake, Haumea, and countless other icy bodies. The Kuiper Belt extends from about 30 times Earth's distance from the Sun to about 50 times that distance. It contains an estimated hundreds of thousands of objects larger than 60 miles across, and perhaps trillions of smaller objects. But again, don't be fooled by the numbers. The Kuiper Belt is not dense. It's less dense than the asteroid belt, which we already established is almost entirely empty. The Kuiper Belt objects are scattered across an enormous three-dimensional shell of space. If you flew through it, you would see nothing but stars. Pluto, once considered the 9th planet, is a small icy world about 1,473 miles across. That's smaller than Earth's moon. It was discovered in 1930 by Clyde Tombaugh, a young astronomer searching for a predicted Planet X. Pluto held its planetary status for 76 years until 2006, when the International Astronomical Union reclassified it as a dwarf planet. When New Horizons flew past in July 2015, it revealed a complex world far more interesting than anyone expected. Mountains of frozen nitrogen tower miles into the thin atmosphere. A vast heart-shaped plain called Sputnik Planitia, filled with slowly churning nitrogen ice, dominates one hemisphere. The ice in this basin flows like a glacier, though imperceptibly slowly. Glaciers of nitrogen ice creep down from the surrounding mountains. Hazes layer the atmosphere, creating a blue ring around the limb of the planet when seen against the sun. Pluto has 5 known moons. Charon, the largest, is so big relative to Pluto that the two are sometimes called a double dwarf planet. They orbit a point in space between them rather than Pluto being the clear center. Charon is about 753 miles across, more than half Pluto's diameter. Its surface is water ice, stained red at the poles by organic compounds called tholins. But Pluto is alone, utterly, profoundly alone. At its average distance from the Sun, Pluto is about 3.7 billion miles away. The Sun from Pluto appears about 1,000 times dimmer than it does from Earth. Noon on Pluto is about as bright as twilight on Earth. The other Kuiper Belt objects are millions or billions of miles away. Pluto drifts through a frozen darkness, accompanied only by its moons. And the journey there, New Horizons, the fastest spacecraft ever launched from Earth, took 9.5 years to reach Pluto. 9.5 years of crossing nothing. The spacecraft was moving at over 36,000 miles per hour when it left Earth, and it still took nearly a decade. Beyond Pluto, the Kuiper Belt continues. Eris, discovered in 2005, is slightly smaller than Pluto, but more massive. It orbits at an average distance of about 6.3 billion miles from the Sun, nearly twice as far as Pluto. At its most distant, Eris is over 9 billion miles away. Makemake, Haumea, Quaoar, Sedna. These are the scattered denizens of the outer solar system, icy worlds drifting in eternal darkness. The outer solar system teaches us something fundamental about the nature of space. Distance is not just a number. Distance is time. Distance is isolation. Distance is the cold reality that separates one island of matter from another. When you look at those diagrams with planets clustered cozily around the Sun, remember what we've learned. The reality is vastly, terrifyingly emptier than any picture could show. The planets are islands in an ocean of nothing. And the nothing is almost all there is. The edge of everything. Where our solar system ends. Most people think Neptune marks the edge of the solar system. It doesn't. Not even close. Neptune is where the major planets end, but the Sun's gravitational influence extends vastly further. The true solar system is far larger than any diagram has ever shown you, and it's emptier than you can possibly imagine. First, let's be clear about what defines the edge of the solar system. It's not a sharp boundary. There's no line painted across space, no sign that says you are now leaving the solar system. Space doesn't have a fence marking where our neighborhood ends and interstellar space begins. Instead, there are several ways to think about the edge, each giving a different answer. One definition is the heliopause. To understand this, you need to understand the solar wind. The Sun doesn't just emit light and heat, it also constantly streams charged particles outward in all directions. This is the solar wind, a flow of protons and electrons and heavier ions racing away from the Sun at tremendous speeds. Near Earth, the solar wind travels at about 1 million miles per hour. That's fast enough to cross the distance from Earth to the Moon in about 15 minutes. The solar wind isn't gentle. It's powerful enough to push back against the thin gas that fills interstellar space. As the solar wind flows outward, it creates a bubble around the Sun called the heliosphere. Inside this bubble, the Sun's influence dominates. The particles come from our star. The magnetic field is shaped by our star. We are, in a very real sense, inside the Sun's extended atmosphere. But the solar wind weakens as it spreads out. The further from the sun it travels, the more diffuse it becomes. Eventually, at some tremendous distance, it becomes so weak that it can no longer push back against the interstellar medium. That's where the heliosphere ends. That boundary is called the heliopause. Before reaching the heliopause, the solar wind encounters something called the termination shock. This is where the solar wind abruptly slows from supersonic to subsonic speeds. Imagine a jet plane slowing from faster than sound to slower than sound. There's a shock wave. The same thing happens to the solar wind at the termination shock. The particles slow down, heat up, and become turbulent. Between the termination shock and the heliopause lies the heliosheath, a region of slow, hot, turbulent solar wind. This is the outermost layer of the sun's domain, the last zone where our star's influence can still be felt. Voyager 1 crossed the termination shock in December 2004, about 94 astronomical units from the sun. Voyager 2 crossed it in August 2007, about 84 astronomical units out. The difference in distance tells us that the heliosphere isn't a perfect sphere. It's distorted by the sun's motion through the galaxy, pushed in on one side and stretched out on the other. Voyager 1 crossed the heliopause in August 2012. Voyager 2 crossed it in November 2018. Both spacecraft detected the transition clearly. The density of solar wind particles dropped. The density of cosmic rays from interstellar space increased. The magnetic field changed direction. The Voyagers had left the sun's protective bubble and entered the galaxy. By this measure, the edge of the solar system is about 11 to 12 billion miles from the sun. That's about 120 astronomical units. Light takes about 16 to 17 hours to travel that far. But even beyond the heliopause, the solar system isn't over. There's another definition of the edge, the limit of the sun's gravitational influence. Gravity has no hard boundary. It extends infinitely, getting weaker with distance but never reaching zero. The sun's gravity reaches out across the light years, growing fainter but never disappearing entirely. However, at some point, the sun's gravity becomes so weak that other forces dominate. The gravity of nearby stars, the general gravitational pull of the galaxy, the slow tides of galactic rotation. At some distance, an object is no longer truly bound to the sun. It might be influenced by our star, but it's not owned by it. That gravitational boundary is roughly defined by the Oort cloud, the hypothetical shell of icy objects that surrounds the solar system at almost unimaginable distances. The Oort cloud is named after Dutch astronomer Jan Hendrik Oort, who proposed its existence in 1950. Oort was studying long-period comets, those visitors from the outer darkness that appear in our skies every few thousand or few million years. These comets puzzled astronomers because they came from all directions. The planets and asteroids and short-period comets all orbit roughly in the same plane, the ecliptic. But long-period comets came from above, below, every angle imaginable. Oort realized that these comets must originate from a spherical shell surrounding the solar system. If they came from a disk like the planets, they would all approach from roughly the same plane. But they didn't. They came from everywhere, which meant their source must be everywhere around us. A sphere. He calculated that this shell must be tremendously far away, perhaps 50,000 to 100,000 astronomical units from the sun. At those distances, the comets would be barely held by the sun's gravity, easily disturbed by the gravitational influence of passing stars or the tidal forces of the galaxy itself. When a star passes within a few light years of our solar system, its gravity can nudge Oort cloud objects from their stable orbits. Some are flung outward, lost to interstellar space forever. Others are nudged inward, beginning the long fall toward the sun that will eventually bring them into the inner solar system as comets. The journey inward takes millions of years. An Oort cloud object disturbed by a passing star might fall toward the sun for 3 million years before finally rounding our star and heading back out. By the time we see a long period comet, the star that disturbed it has long since moved on, continuing its own journey around the galaxy. The Oort cloud has never been directly observed. No telescope has imaged an Oort cloud object in its distant orbit. The objects are too small, typically just a few miles across. They're too far, tens of billions of miles away. And they're too dim, reflecting almost no light from a sun that appears as just another star in their sky. We can only infer the cloud's existence from the comets it sends us. But if the Oort cloud exists, and virtually all astronomers believe it does, then it represents the true edge of the solar system. It's a ghost shell, a spherical envelope of ancient ice, extending up to 1.6 light years from the sun. 1.6 light years. The light leaving the sun right now won't reach the outer edge of the Oort cloud for about a year and a half. If the sun exploded this instant, the outermost comets in our solar system wouldn't know about it until late next year. The Oort cloud is estimated to contain perhaps 1 trillion objects larger than half a mile across, and countless trillions of smaller icy bodies. The total mass is uncertain, but estimates range from about 5 to 100 Earth masses. That sounds like a lot of material, but remember the volumes involved. The Oort cloud occupies a spherical shell with a volume of about 3.4 times 10 to the 39 cubic miles. Spread those trillions of objects through that volume, and each one is surrounded by billions of cubic miles of empty space. If you flew through the Oort cloud, you would see nothing. Stars in every direction, yes, but no Oort cloud objects. They're far too scattered to be visible. The space between the heliopause and the Oort cloud is even emptier. From about 12 billion miles to about 186 billion miles, there's almost nothing. The scattered disk contains some objects on highly elliptical orbits, frozen worlds like Sedna that swing far out beyond the Kuiper belt before returning. But these are rare. A handful of objects spread across trillions of cubic miles. This is the truest expression of the solar system's emptiness. Not the gaps between planets, as vast as those are. The true emptiness lies between the organized planetary system and the ghost shell at the edge. Trillions of miles of cold vacuum, dark except for starlight, empty except for the occasional wandering object. In our basketball scale model, the inner edge of the Oort cloud would be about 30 miles from the basketball sun. The outer edge would be about 1,600 miles away. 1,600 miles. That's roughly the distance from New York to Denver, from a basketball to a point 1,600 miles away. Let's talk about the spacecraft we've sent toward this emptiness, because they're humanity's first and only emissaries to the outer reaches. Voyager 1 and Voyager 2 were launched in the summer of 1977. The mission took advantage of a rare planetary alignment that occurs only once every 175 years. In this alignment, Jupiter, Saturn, Uranus, and Neptune were positioned so that a spacecraft could visit each one in sequence, using each planet's gravity to boost its speed and redirect its trajectory toward the next target. This technique, called gravity assist, allows spacecraft to gain tremendous speed without using fuel. The spacecraft essentially borrows energy from the planet's motion around the Sun. It's a cosmic slingshot that makes outer solar system exploration possible. Voyager 2 launched first, August 20th, 1977. Voyager 1 launched 16 days later, on September 5th. Despite launching second, Voyager 1 was placed on a faster trajectory that would take it to Jupiter and Saturn more quickly. Voyager 1 flew past Jupiter in March 1979, returning stunning images of the giant planet and its moons. It discovered volcanic activity on Io, the first evidence of active volcanism anywhere beyond Earth. It photographed Europa's cracked ice surface, hinting at the ocean beneath. It captured images of Jupiter's ring system, too faint to be seen from Earth. At Saturn, Voyager 1 made a close flyby of Titan, Saturn's largest moon. Scientists were intensely interested in Titan because it was known to have a thick atmosphere. The close flyby meant Voyager 1 would be deflected out of the ecliptic plane and couldn't visit Uranus or Neptune. But the scientific value of studying Titan was deemed worth the sacrifice. Voyager 2 followed a different path. After visiting Jupiter and Saturn, it continued to Uranus, arriving in January 1986. Then, it travelled onto Neptune, arriving in August 1989. To this day, Voyager 2 remains the only spacecraft to have visited Uranus and Neptune. No other missions to these ice giants are currently in flight. After their planetary encounters, both Voyagers continued outward into the darkness. They were travelling fast, over 35,000 miles per hour, and nothing was going to stop them. The Voyagers were designed to last about 5 years, long enough to complete their planetary flybys, but they kept working. Their plutonium power sources continued generating electricity. Their instruments continued functioning. Their radio transmitters continued beaming data back to Earth. As of 2024, both Voyagers are still operating, nearly 50 years after launch. Voyager 1 is about 15 billion miles from Earth, the most distant human-made object in existence. Voyager 2 is about 12.6 billion miles away. The signals from the Voyagers are impossibly faint by the time they reach Earth. The spacecraft transmit with only about 23 watts of power, roughly the same as a refrigerator light bulb. By the time these signals travel 15 billion miles, they've spread out so much that the power reaching Earth is measured in billionths of a watt. NASA uses enormous radio dishes, part of the Deep Space Network, to detect these whispers from the void. The largest dish, in Canberra, Australia, is 230 feet across. Even with this massive antenna, receiving data from the Voyagers takes hours for just a few kilobytes of information. The Voyagers' power is fading. The plutonium in their radioisotope thermoelectric generators decays over time, producing less and less electricity each year. NASA has already shut down heaters and non-essential instruments to conserve power. By the mid-2030s, probably around 2035 or 2036, there won't be enough power to operate any scientific instruments. The Voyagers will go silent, but they'll keep traveling. The void doesn't require power to cross. The Voyagers will continue their journey for hundreds of thousands of years, drifting through the darkness long after their batteries have died and their circuits are frozen. At their current speeds, the Voyagers would take about 500 years to reach the inner edge of the Oort cloud. They would take about 30,000 years to pass through the Oort cloud and reach the outer edge. 30,000 years. Human beings were still sharing the planet with Neanderthals 30,000 years ago. We hadn't invented agriculture or writing or cities. We were nomadic hunter-gatherers, making stone tools and painting on cave walls. All of recorded history, everything we call civilization, fits into the last 5,000 years. The Voyager's journey through the Oort cloud will take 6 times longer than the entire duration of human civilization to date. The Voyagers will outlast everything we've ever built. They'll outlast our cities and our nations. They might outlast our species. Long after humanity is gone, whatever humanity becomes, the Voyagers will still be drifting through the outer darkness, carrying our message to the stars. And they do carry a message. Each Voyager spacecraft has a golden record attached to its side. These are actual phonograph records, 12-inch discs made of gold-plated copper. They were designed by a committee chaired by Carl Sagan, the astronomer who, more than anyone else, brought the wonders of the cosmos to the general public. The golden records contain sounds and images from Earth, greetings in 55 languages, from ancient Sumerian to modern English, samples of music from around the world, including Bach, Mozart, Beethoven, Chuck Berry, and traditional music from Peru, Japan, Bulgaria, and dozens of other cultures. Natural sounds: thunder, wind, rain, surf, birds, whales, frogs. The records also contain 116 images encoded in analog form, photographs of Earth, of humans, of our science and our culture, diagrams showing human anatomy, the structure of DNA, the location of our solar system in the galaxy. Instructions for playing the record are etched into the cover in a language based on fundamental physics, using the transition frequency of hydrogen atoms as a universal constant. The records were designed to last 1 billion years in the cold of interstellar space. The gold plating protects against erosion. The vacuum preserves the grooves. 1 billion years from now, if some civilization finds a Voyager, they should be able to play the record and hear human voices, human music, the sounds of our world. Will anyone ever find them? Almost certainly not. The Voyagers are not aimed at any star. They're heading out of the solar system in directions determined by their planetary encounters, not toward any destination. Voyager 1 will pass within 1.6 light years of a star called Gliese 445 in about 40,000 years. But that's a relatively close approach by interstellar standards, and it still won't come within hundreds of billions of miles of the star itself. Space is vast. The Voyagers are tiny. The chances of an alien civilization stumbling across them are essentially zero. But that was never really the point. The golden records were a message in a bottle thrown into an infinite ocean. We sent them not because we expected an answer, but because the act of sending them said something about who we are. We're a species that wanders. We are a species that reaches out. We are a species that hopes, even when hope seems futile. As Carl Sagan wrote, the launching of this bottle into the cosmic ocean says something very hopeful about life on this planet. In 1990, as Voyager 1 leaves the planetary solar system, Sagan convinced NASA to turn the spacecraft's camera around for one last look at Earth. By that point, Voyager 1 was about 3.7 billion miles from home. Earth, from the distance, was a tiny dot, less than 1 pixel in size. The image became known as the pale blue dot. It shows Earth as a tiny point of light, almost lost in the background radiation, suspended in a beam of scattered sunlight. Everything we've ever known, every human who ever lived, every city that ever stood, exists on that barely visible speck. Sagan reflected on this image with characteristic eloquence. He noted that our planet is a lonely speck in the great enveloping cosmic dark. He pointed out that every saint and sinner in human history lived on that mote of dust. He suggested that the pale blue dot underscores our responsibility to deal more kindly with one another and to preserve the only home we've ever known. The pale blue dot is more than a photograph. It's a perspective. It shows us our true place in the cosmos. A tiny island of warmth and light in an ocean of cold darkness. The emptiness that surrounds us is not hostile, but it is indifferent. It doesn't care about our ambitions or our conflicts. It simply is. Let me also tell you about Pioneer 10 and Pioneer 11, the spacecraft that blazed the trail the Voyagers followed. Pioneer 10 was launched in March 1972. It was the first spacecraft to travel through the asteroid belt and the first to make a close flyby of Jupiter. Pioneer 11 followed in April 1973, visiting both Jupiter and Saturn. These were truly pioneering missions, the first human objects sent to the outer solar system. Before Pioneer 10, no one knew for certain whether a spacecraft could survive the asteroid belt. Some scientists worried that the density of material might be enough to destroy any probe. Pioneer 10 proved them wrong, sailing through the belt without incident. Both Pioneer spacecraft are now beyond the orbit of Neptune, heading outward into the void. Pioneer 10 is about 12.8 billion miles from Earth. Pioneer 11 is about 10 billion miles away, but we've lost contact with both of them. Pioneer 11's last signal was received in November 1995. Pioneer 10's last signal was in January 2003. Their power ran out, their transmitters went silent, and now they drift through the void in eternal silence. The Pioneer spacecraft carry a simpler message than the Voyager's golden records. Each has a gold anodized aluminum plaque attached to its antenna support struts. The plaque shows the figures of a man and a woman, drawn to scale against an outline of the spacecraft. It shows the location of our sun relative to 14 pulsars, rapidly rotating neutron stars whose precise timing could serve as cosmic landmarks. It shows a schematic of the solar system with the spacecraft's trajectory marked. These plaques were humanity's first intentional messages to extraterrestrial intelligence. They were designed by Sagan and astronomer Frank Drake, with artwork by Sagan's wife Linda Salzman Sagan. They're simple, elegant, and probably futile, but they exist. They're out there right now, drifting through the darkness, carrying our hello. And then there's New Horizons, the most recent addition to our fleet of interstellar ambassadors. New Horizons launched in January 2006 on a mission to explore Pluto. It was the fastest spacecraft ever launched from Earth, leaving our planet at over 36,000 miles per hour. Even at that tremendous speed, it took 9.5 years to reach Pluto. The Pluto flyby in July 2015 was a triumph. New Horizons revealed a world far more complex than anyone expected. Mountains of frozen nitrogen, glazes of nitrogen ice, a thin but significant atmosphere, evidence of recent geological activity on a world that should be frozen solid. After Pluto, New Horizons continued into the Kuiper Belt. In January 2019, it flew past a small object called Arakoth, previously known as Ultima Thule. Arakoth is about 22 miles long and shaped like a snowman. Two lobes stuck together in a gentle collision billions of years ago. It's the most distant object ever visited by a spacecraft. New Horizons is still operating, still returning data. As of 2024, it's about 5.5 billion miles from Earth and continuing outward. It will eventually follow the pioneers and voyagers into interstellar space, though it will take decades to reach the heliopause, 5 spacecraft. In over 50 years of space exploration, we've sent exactly 5 objects toward the stars. All 5 are traveling at speeds that will take tens of thousands of years to clear the Oort cloud. All 5 will drift for millions of years through interstellar space, silent messengers from a world they left long ago. Let's talk about the light travel times at the edge of the solar system, because they reveal something profound about the nature of space and time. Light from the sun takes about 8 minutes to reach Earth. It takes about 4 hours to reach Neptune, where the major planets end. To reach the heliopause, where the Voyagers now are, light takes about 16 to 17 hours. That means when we receive signals from Voyager 1, we're hearing about events that happened almost a day ago. Any command we send takes another 17 hours to arrive. A round-trip communication takes nearly a day and a half. To reach the inner edge of the Oort cloud, light takes about 2 to 3 weeks. To reach the outer edge, light takes about 1.5 to 2 years. If the sun were to explode right now, not that it will, but hypothetically the outermost objects in our solar system wouldn't see the flash for nearly 2 years. They would continue orbiting a star that no longer existed, illuminated by phantom light from a dead sun. This time, lag creates something profound: effective isolation. At the distances of the Oort cloud, real-time communication becomes impossible. Any message takes weeks or months or years to arrive. Any response takes equally long to return. You cannot have a conversation across these distances. You can only send messages and wait. Consider what this means for any hypothetical future exploration. If humans ever send a crewed mission to the Oort cloud, which would require technologies far beyond what we currently possess, those explorers would be cut off from Earth in ways no human has ever experienced. An emergency on such a mission would be answered by silence. A request for advice would take months to receive a response. News from home would arrive weeks or years after it happened. Holidays would pass, children would be born, people would die, and the explorers wouldn't know about any of it until long after. The crew would have to become autonomous in every way. They couldn't rely on mission control. They couldn't call for help. They would have to solve every problem themselves, make every decision themselves, live or die by their own choices. The emptiness would enforce independence. The void would create complete isolation. Let's put the Oort cloud in perspective by comparing it to the nearest star. Proxima Centauri, the closest star to the Sun, is about 4.24 light-years away. That's about 25 trillion miles. It's a small red dwarf star, part of a triple star system that also includes Alpha Centauri A and Alpha Centauri B. The outer edge of the Oort cloud is about 1.6 light-years away. That means the Oort cloud extends about 38% of the way to the nearest star. This is remarkable. Our solar system's outermost boundary reaches more than a third of the way to our nearest neighbor. The space between stars isn't as empty as you might think, at least not at the edges. But here's the other side of that coin. Between the outer edge of the Oort cloud and Proxima Centauri, there's still about 2.6 light-years of nothing. Pure interstellar space. No sun to orbit, no planets to visit, no gravitational anchor, just darkness and cold and the distant light of stars. And even that void might not be entirely empty. Proxima Centauri might have its own Oort cloud, extending back toward us. The Alpha Centauri system might have a cometary shell that overlaps with ours. The space between stars might be peppered with rogue objects, icy bodies ejected from their home systems and wandering between the stars forever. In 2017, astronomers discovered an object called Oumuamua, the first confirmed interstellar visitor to pass through our solar system. It came from outside, passed close to the sun, and then headed back out into interstellar space. Its origins are unknown. It might have been ejected from another star system billions of years ago. It might have been wandering between the stars ever since. In 2019, another interstellar object was discovered. Comet Borisov. This one was clearly a comet, trailing a tail of gas and dust. It too passed through our solar system and left, returning to the darkness between stars. These objects suggest that interstellar space isn't entirely empty. There may be trillions of rogue objects drifting between the stars, orphans from the galaxy's billions of planetary systems. But even trillions of objects, spread across the volume of the galaxy, would be impossibly sparse. You could travel for millions of years without encountering one. The emptiness is the rule. Matter is the exception. And the solar system, despite all its planets and moons and asteroids and comets, is just a slightly denser pocket of nothing in an infinite sea of void. The solar system ends not with a bang, but with a fade. There's no wall, no boundary marker, no edge you can stand on and look out at interstellar space. There's just a gradual thinning, a slow fade from something to nothing, from the sun's domain to the galaxy's indifference. Somewhere out there, perhaps a light year and a half from the sun, an icy body orbits. It's been there for 4.5 billion years since the solar system formed. It's never been warmed by the sun. It's never felt the gravitational tug of the planets. It's barely held by the sun's gravity, just barely part of our cosmic family. Beyond that body, there are more. And beyond them, eventually, there are none. The sun's influence ends. Interstellar space begins. And the void stretches on toward the next star, and the next, and the next, across a galaxy that is itself mostly empty, across a universe that is almost entirely nothing. The edge of the solar system is the edge of everything we know. Beyond it lies the unknown, and the unknown is vast beyond imagining. The meaning of nothing. Why emptiness matters. So the solar system is mostly empty. The distances between objects are vast beyond human comprehension. The void stretches for trillions of miles in every direction. Why should any of this matter? Why care that space is mostly nothing? Because the emptiness isn't just a fact. It's the reason we exist at all. First, the emptiness tells us something about how the solar system formed. 4.5 billion years ago, the sun and planets emerged from a collapsing cloud of gas and dust. This cloud, called the solar nebula, contained all the raw materials for our cosmic neighborhood. But from the beginning, the cloud was mostly empty. Even at its densest, the solar nebula was a near-perfect vacuum by Earth standards. If you could have stood in the middle of that primordial cloud, you would have seen nothing but blackness punctuated by distant stars. The gas and dust particles were separated by distances far larger than themselves. A cubic inch of the densest part of the nebula contained fewer particles than a cubic inch of the best laboratory vacuum on Earth today. Gravity slowly pulled this sparse material together, concentrating it in certain regions while leaving others empty. Where matter gathered, more matter followed, drawn by the increasing gravitational pull. Where emptiness reigned, emptiness persisted, because there was nothing to attract anything. The sun formed at the center, where gravity concentrated the most mass. Over about 100,000 years, the core of the nebula collapsed, growing hotter and denser, until hydrogen atoms began fusing into helium. A star was born. But even as the sun ignited, the rest of the nebula remained sparse. There simply wasn't enough material to fill the space. The planets formed in a disk around the young sun, where orbiting material could collide and stick together. Dust grains became pebbles, pebbles became boulders, boulders became planetesimals, objects miles across. Planetesimals became protoplanets. Over millions of years, the largest bodies swept up the debris around them, growing into the planets we know today. But this process was inefficient. Most of the original disk material was either pulled into the sun, blown away by the young star's intense radiation, or scattered into the outer reaches of the solar system. The planets captured only a tiny fraction of the available mass. The rest was lost or dispersed. This is why the solar system is mostly void. It's not that the emptiness was created. It's that the emptiness was never filled. The original material was sparse, and gravity concentrated it into islands rather than spreading it evenly. The emptiness isn't a failure. It's a feature. It's how gravity works on the scale of star systems. Second, the emptiness is why planets exist at all. This sounds paradoxical. How can emptiness create worlds? But think about it this way. If the solar nebula had been dense, if matter had been spread evenly throughout the region that became the solar system, gravity would have pulled everything into the sun. There would be no planets, no moons, no asteroids, just a single massive star made of all the available material, perhaps a star much larger than our sun, burning hotter and dying faster. It is precisely because the nebula was sparse that some material could orbit rather than fall inward. The emptiness between particles meant that gravity couldn't capture everything instantly. Some material had time to acquire angular momentum, that tendency to move sideways rather than straight down. This sideways motion allowed particles to miss the central mass, to swing around it rather than falling into it. The planets are survivors. They're made of material that avoided falling into the sun by having just enough sideways motion to miss. The Earth exists because 4.5 billion years ago, the particles that would become our world were moving fast enough to orbit rather than plunge into the growing sun. And that sideways motion was possible only because the nebula was mostly empty, allowing particles to orbit freely rather than colliding constantly. In a dense environment, collisions would have robbed particles of their angular momentum, slowing their orbits and causing them to spiral inward. But in the sparse nebula, collisions were rare enough that angular momentum could be preserved, allowing matter to settle into stable orbits. Every world in the solar system, including Earth, exists because of the void. The emptiness between particles in the original nebula is the reason we're here. Third, the emptiness protects us. If the solar system were crowded, Earth would be constantly bombarded by debris. Asteroids and comets would strike us regularly, sterilizing the surface, boiling away the oceans, making the evolution of complex life difficult or impossible. Consider what bombardment was like early in Earth's history. During the late heavy bombardment, about 4 billion years ago, the inner solar system was pummeled by debris left over from planetary formation. Impact craters from this era cover the moon's surface. Earth was hit even harder, but our planet's active geology has erased most of the evidence. Life may have arisen multiple times during this period, only to be wiped out by the next major impact. It wasn't until the bombardment subsided, until the solar system had cleared most of its debris, that life could gain a permanent foothold. Today, the vast distances between objects mean that collisions are rare. Most asteroids stay in their orbits in the belt between Mars and Jupiter, circling the Sun for billions of years without encountering anything. Most comets remain in the Kuiper belt or the Oort cloud, frozen and distant. The emptiness acts as a buffer, isolating us from most potential impactors. This doesn't mean Earth is safe. Major impacts have happened and will happen again. The dinosaurs died because a 6-mile asteroid found its way to our planet 66 million years ago. The Tunguska event in 1908, probably caused by a small asteroid or comet fragment, flattened 800 square miles of Siberian forest. The Chelyabinsk meteor in 2013 injured over 1,000 people when it exploded over Russia. But such events are rare precisely because the solar system is mostly empty. The void gives lifetime to evolve between catastrophes. Complex creatures like dinosaurs had over 160 million years to evolve and diversify before their extinction event. Mammals have had 66 million years since then. The emptiness provides the stability that evolution requires. Jupiter helps too. Its massive gravity attracts and captures many comets and asteroids that might otherwise threaten the inner planets. In 1994, we watched Comet Shoemaker-Levy 9 break apart and slam into Jupiter, a series of impacts that would have been catastrophic if they had struck Earth. Jupiter absorbed the blow as it has absorbed countless blows over billions of years. Jupiter acts as a cosmic vacuum cleaner, sweeping up debris that could endanger Earth. Some astronomers believe that life on Earth may owe its existence to Jupiter's protection. Without the giant planet, our world might have been struck so often that complex life could never have evolved. But even Jupiter's protection works because of the emptiness. There's room for Jupiter to sweep objects out of dangerous orbits, room for it to absorb impacts that might otherwise reach us. In a crowded solar system, even Jupiter couldn't protect us. The emptiness is part of our cosmic defense system. The void is not hostile, it's protective. Fourth, the emptiness makes exploration possible. If the solar system were crowded, navigating through it would be treacherous. Spacecraft would need to dodge debris constantly. Trajectories would be unpredictable, disturbed by countless small gravitational tugs from nearby objects. Reaching other planets would be far more difficult than it already is. Instead, spacecraft travel through almost perfect vacuum. They follow smooth trajectories governed by the gravity of large, predictable objects. The sun, the planets, occasionally a moon. The emptiness is what makes orbital mechanics work, what allows us to calculate precisely where a spacecraft will be years in advance. This predictability is essential for space exploration. When we launch a mission to Mars, we calculate the trajectory months or years in advance. We know where Mars will be when the spacecraft arrives. We know how much fuel will be needed for course corrections. We know, within seconds, when the spacecraft will enter Mars orbit or land on the surface. This precision is possible only because space is empty. If there was significant debris between Earth and Mars, we couldn't predict our spacecraft's path so accurately. Random encounters with small objects would alter the trajectory in unpredictable ways. Navigation would become a matter of luck rather than calculation. The emptiness is what makes the solar system navigable. It's the clear highway between destinations. Fifth, the emptiness has profound implications for the search for life. If life exists elsewhere in the solar system, it's isolated. Any microbes in the subsurface ocean of Europa are separated from Earth by about 400 million miles at closest approach, over 500 million miles at farthest. Any life on Enceladus is about 750 million miles away on average. Any organisms in the methane lakes of Titan are nearly 1 billion miles distant. The emptiness means that if life exists elsewhere in our solar system, it almost certainly arose independently. The distances are too great for organisms to travel between worlds under normal circumstances. Microbes can't swim through vacuum. Spores can't drift across hundreds of millions of miles of nothing. There is a theory called panspermia, which suggests that life might spread between worlds via meteorites. When an asteroid strikes a planet, it can blast rocks into space. If those rocks contain microorganisms, and if the microorganisms can survive the journey through space and the fiery entry into another world's atmosphere, life might transfer from one planet to another. But even if panspermia occurs, it's extremely rare. The emptiness makes it so. Rocks blasted off one planet almost never encounter another planet. They orbit the sun for millions or billions of years, drifting through nothing. The vast majority will never strike another world. The void ensures that each planet is effectively an isolated experiment in biology. This matters because it tells us something about how common life might be in the universe. If we find that life arose independently on multiple worlds in our solar system, that would suggest life arises easily wherever conditions permit. Life would be almost inevitable on any world with the right chemistry and energy sources. If we find that Earth is the only world with life, even after thoroughly searching places like Mars, Europa, and Enceladus, that might suggest life is rare. We might be a cosmic accident, a 1 in a trillion fluke, alone in an empty universe. The emptiness creates natural experiments. Each potentially habitable world is isolated, evolving in its own way, untouched by the others. If we can visit these worlds and study them, we'll learn something profound about the nature of life itself. Sixth, the emptiness connects to one of the deepest questions in science, the Fermi paradox. In 1950, the physicist Enrico Fermi was having lunch with colleagues when the conversation turned to extraterrestrial life. Given the age and size of the universe, given the billions of stars in our galaxy alone, surely intelligent life should have evolved elsewhere. Surely some of those civilizations should have developed space travel. Surely, given enough time, they should have spread throughout the galaxy, visiting every star system, including ours. But we see no evidence of alien visitors. No spacecraft. No signals, no artifacts, nothing. Where is everybody? Fermi asked. This question, now known as the Fermi paradox, has puzzled scientists for over 70 years. Dozens of explanations have been proposed. Perhaps intelligent life is rare. Perhaps civilizations destroy themselves before achieving interstellar travel. Perhaps they're hiding. Perhaps they're here, but we don't recognize them. The emptiness of our own solar system hints at another possible answer. Space is not just big. It's impossibly, overwhelmingly, suffocatingly big. The distances between stars make the distances within our solar system look trivial by comparison. Proxima Centauri, the nearest star, is about 4.24 light-years away. That's about 25 trillion miles. At the speed of our fastest spacecraft, It would take about 70,000 years to get there. Even if we could travel at 10% of the speed of light, a feat far beyond current technology, the journey would take over 40 years. And Proxima Centauri is the closest star. Most stars in our galaxy are hundreds or thousands of light years away. The galaxy is 100,000 light years across. Even at the speed of light, crossing it would take longer than our species has existed. Perhaps alien civilizations exist, but they're isolated by the same emptiness that isolates us. Perhaps the distances between stars are simply too great for meaningful contact. Perhaps the universe is full of life, but that life is trapped on isolated islands, unable to bridge the cosmic void. Each civilization might build radio telescopes and send messages into the darkness. Each might launch probes toward nearby stars, but the probes take millennia to arrive. The messages take years or centuries. Communication across such distances is barely possible. Conversation is impossible. The emptiness of our solar system is a microcosm of the emptiness of the universe, and that emptiness might be the reason we feel so alone. Seventh, the emptiness gives us perspective. When we understand how small the planets are compared to the spaces between them, we see our world differently. Earth is not a large planet in a cozy solar system. It's a tiny speck in an immense void. Our entire civilization, everything we've ever built, everyone who's ever lived, exists on a pale blue dot surrounded by trillions of miles of nothing. This perspective is humbling. It shrinks our conflicts and achievements to their proper scale. The borders we fight over, the differences we exaggerate, the status we crave, all of it plays out on a tiny stage floating in an ocean of emptiness. Consider how much energy we spend on things that, from a cosmic perspective, are utterly insignificant. Wars fought over lines on a map that can't be seen from space. Fortunes accumulate that will be forgotten in a century. Fame sought that will fade while the stars still burn. The void doesn't care about our politics or our religions or our economic systems. The emptiness has no opinion about which nations rise and which fall. The cosmos proceeds according to its own rules, indifferent to everything we consider important. This sounds bleak, but it can also be liberating. If the universe doesn't care about our petty divisions, maybe we shouldn't either. If our planet is a tiny island in an infinite sea, maybe we should focus on taking care of that island rather than fighting over it. If we're all we've got in this corner of the cosmos, maybe we should act like it. But this perspective is also inspiring. Despite our smallness, we've figured out the scale of the void. We've sent spacecraft billions of miles into it. We've photographed distant worlds. We've mapped the solar system from the sun to the Kuiper Belt and beyond. No other species on Earth has done this. For all we know, no other species in the galaxy has done this. We may be tiny, but we are unique. We have looked into the abyss, and instead of despair, we have felt wonder. We are small, but we are not insignificant. We've turned our small eyes toward the vast darkness and begun to understand it. That's remarkable. Eighth, the emptiness is the future. If humanity survives and spreads beyond Earth, we will do so into the void. There is no other option. The moon is 3 days away across empty space. Mars is months away. The outer planets are years away. Any destination beyond the solar system is centuries or millennia away with foreseeable technology. Space exploration is fundamentally about crossing emptiness. Every mission is a journey through nothing to reach something. The void is not an obstacle to be avoided, but a medium to be traversed. Consider what it would mean to become a truly spacefaring species. We would have to master the art of survival in emptiness. Our ships would have to carry everything needed for years or decades: air, water, food, spare parts, medical supplies. Our crews would have to remain healthy and sane through months or years of isolation, separated from Earth by millions or billions of miles. The void would shape our technology. We would need better propulsion systems to cross the emptiness faster. We would need better recycling systems to survive without resupply. We would need better communication systems to stay connected across the gulf. The void would shape our psychology. We would have to develop new ways of coping with isolation. New ways of maintaining community across distances where real-time conversation is impossible. New ways of thinking about home when home is a tiny point of light in an alien sky. The void would shape our philosophy. We would have to grapple with questions of meaning in an indifferent cosmos. Questions of connection when connection is attenuated by millions of miles. Questions of identity when the cultures we left behind are years out of date. And the void is patient. It will wait for us. Unlike Earth's oceans, which can swallow ships and leave no trace, the void preserves. There's no weather in space to erode metal, no organisms to decompose plastic, no oxygen to rust steel. Our artifacts will last essentially forever. The emptiness is a canvas. Humanity has barely begun to paint on it. Let me tell you what the solar system would look like if it weren't mostly empty. Imagine a version where the planets were packed closely together, where you could see multiple planets in the sky at once, each visible as a disk rather than a point of light. Where the asteroid belt was truly dense, a visible ring of rocks between Mars and Jupiter that glittered in the sunlight. Where moons were clustered so tightly that they dominated their planet's sky. This version would be more photogenic. It would make for better diagrams. It would feel more substantial, more populated, more like a real place rather than a vast emptiness with occasional specks. But this version would be chaotic. Gravitational interactions between closely spaced planets would destabilize orbits. Worlds would tug on each other, their orbits slowly shifting, sometimes intersecting. Collisions would be common on astronomical timescales. No orbit would be stable for long. The solar system would be a cosmic demolition derby. Worlds would smash into each other over millions of years. Debris from these collisions would rain down on survivors. The inner solar system might be sterilized every few million years by cataclysmic impacts. Worse, a dense solar system would be hostile to life in subtler ways. Orbital perturbations would cause climatic instability. A planet's distance from the sun would fluctuate, causing wild swings in temperature. Axial tilts would wander, disrupting seasons. Ice ages and heat waves would alternate chaotically. Evolution requires stability. Complex life takes hundreds of millions of years to develop. If the environment is disrupted every few million years, complexity never emerges. You might get bacteria, but never fish, never trees, never humans. The emptiness isn't a flaw. It's what makes the solar system habitable. The void provides stability. The nothingness enables life. We should be grateful for the emptiness. Let me also tell you about the silence. Sound doesn't travel through vacuum. In space, there's nothing to carry pressure waves, nothing to vibrate, nothing to transmit noise. Sound requires a medium: air, water, rock. The emptiness provides none of these. On Earth, we're immersed in sound. Even in the quietest places, there's wind rustling through leaves, distant traffic humming, birds calling, insects chirping, the hum of electricity in walls. True silence is almost impossible to find on our planet. Our ears are always hearing something, even if it's just the blood rushing through our own bodies. But in space, silence is the default. The void carries no sound. A rocket's exhaust makes no noise once it leaves the atmosphere. An explosion in space is visible, but inaudible. A spacecraft passes in complete quiet, its only sound the faint vibrations of its own machinery transmitted through its structure. The solar system plays out its drama in absolute silence. Jupiter's storms rage without thunder. Saturn's rings shimmer without whisper. Geysers erupt on Enceladus without hiss. Winds howl on Neptune without sound. If you could stand on the surface of an airless world and watch a meteor strike the horizon, you would see the flash, see the debris rise, see the crater form, but you would hear nothing. The impact would be silent. Only if the ground vibrations reached you, transmitted through the rock beneath your feet, would you sense anything. This silence is profound. It means that the cosmos is essentially a silent movie, a visual spectacle unaccompanied by soundtrack. All the noise we associate with space, the roars and whooshes of science fiction films, is an invention of entertainment. Real space makes no sound at all. The emptiness is not just spatially empty, it's acoustically empty. The void is a realm of absolute silence stretching for billions of miles. Let me give you one final image to carry with you. Picture yourself standing on Earth, looking up at the night sky. You see stars, thousands of them on a clear, dark night. You might see planets too. Venus, blazing near the horizon just after sunset. Mars with its distinctive reddish tint. Jupiter, bright and steady, outshining almost everything. You know now that between you and those points of light lies nothing. Vacuum, emptiness, miles and miles of dark silence, interrupted by nothing, traversed only by light. Now picture yourself at the edge of the solar system, at the outer boundary of the Oort cloud, looking back toward the sun. The sun is a bright star, brighter than any other in the sky, but still just a point of light. You might find it among the thousands of other stars, or you might have to search. It doesn't stand out as dramatically as you might expect. It's just one star among many, distinguished only by its slight brightness. The planets? Invisible. Completely invisible. Even Jupiter, the giant that dominates our night sky, is too small and too far to see from this distance. Even Saturn with its magnificent rings is lost in the sun's glare. The entire planetary solar system, everything from Mercury to Neptune, all the worlds we've named and mapped and dreamed about, is hidden in the light of that one distant star. Your home is there, somewhere. Your entire civilization is there. Everything humanity has ever known exists in the vicinity of that point of light. But you can't see any of it. You can't distinguish Earth from the sun's glow. You can't make out the continents, the oceans, the cities. All of it is invisible, lost in the distance. This is what the solar system looks like from its own edge. Not a grand collection of worlds arranged in majestic order, but a single point of light in an infinite field of similar points. Not a special place marked out for cosmic importance, but an ordinary star with invisible companions. Not a destination, but a distant origin, already receding into the void. The emptiness doesn't just surround the solar system. From most perspectives, the emptiness defines it. We are a point of light and nothing more. And yet, that point of light contains everything we love, everyone we know, every place we've been, every story we've told, every dream we've dreamed. The solar system is mostly nothing, but the something that exists within it. The thin film of warmth and light clinging to a few small rocks orbiting an ordinary star. That something is everything to us. The void stretches in every direction. The emptiness goes on forever. The nothing dominates the something by a ratio of trillions to one. But here, on this one small world, the something is enough. It's enough to build civilizations. Enough to write poetry. Enough to compose symphonies and paint masterpieces and raise children and fall in love. Enough to send robots to other planets and wonder at what they find. Space is mostly nothing, but we are the something. And that makes all the difference. Tonight, if the sky is clear, go outside and look up. See if you can find a planet. Venus might be shining near the horizon in the west. Mars might be visible as a reddish point in the east. Jupiter might be burning bright overhead. When you see that planet, remember what you've learned. That point of light is a world, yes. A world with storms or deserts or rings or moons. But between you and the world is nothing. Millions or billions of miles of absolute vacuum. Cold, dark, silent, empty. The photons hitting your eye left that planet minutes or hours ago. They've been traveling through nothing ever since, crossing the void at the speed of light, traversing the emptiness that makes up almost all of the solar system, until they happen to enter your pupil and trigger a signal in your brain. You're connected to that distant world by nothing. The emptiness is the medium through which you see it. The void is the bridge between your eyes and the cosmos. We live in a solar system made mostly of nothing. We are surrounded by void. We float on a tiny rock in an ocean of emptiness. And yet, we look up. We wonder. We reach out. We send our spacecraft into the darkness and wait years for their reports. We build telescopes to gather ancient light. We write equations to describe the motions of distant worlds. We tell stories about what might be out there, waiting to be discovered. The emptiness defines the solar system, but we define ourselves by our refusal to let it stop us. Space is mostly nothing. We are the something that dares to explore it. Thank you for joining me on this journey through the void. If you found this exploration meaningful, please consider liking this video and subscribing to the channel. Your support helps me continue making these deep dives into the nature of our universe. Remember, the next time someone shows you a diagram of the solar system with planets clustered cozily around the sun, you'll know the truth. The reality is vaster, emptier, and more profound than any diagram can show. The solar system is an abyss with islands. We live on one of those islands, and the abyss stretches on forever. Good night, and sleep well, knowing that the void that surrounds us is also what protects us, enables us, and humbles us. The emptiness is not nothing, it's everything.